Hello guys, welcome to this video. Today we're going to discuss some properties of the spectrum of an operator, and we're going to delve deep into some theorems of holomorphic functions and associated properties. And this is the last video on spectral theory, and if you have made it till here, hats off to you. It's been a long road. It's really tiresome but full on. Now let's get started with this stuff. Let X be a non-trivial complex Banach space, T from X to X be a bounded linear transformation. Now it follows that the spectrum is a subset of complex numbers such that the norm of lambda is less than equals to norm of T. So I should say that mod of lambda rather than norm, because lambda lies in the complex plane. But anyway, so it's essentially saying that spectrum is a subset of the complex disk centered around 0 with radius less than equals to norm of T. And essentially the second idea says that function as we go to as lambda naught or as mod of lambda goes to infinity, then norm of r lambda t goes to 0. And the third idea says that the spectrum is not null. Spectrum of an operator from a complex Banach space to a complex Banach space where t is a bounded linear operator is not null. So let's start. So choose a lambda with the mod of lambda greater than norm of t, and define S to be T by lambda. Now when I choose S to be T by lambda, and norm of S becomes less than 1. Now if the norm of S is less than 1, I can use the Neumann series. I can say that I minus S is invertible, and then formula is given like this. And now I minus S, so lambda times I minus S is equals to lambda I minus T, and hence I can say that lambda I minus T is invertible. And now this from a corollary of the closed mapping theorem, I know that if X and Y are Banach spaces and T is closed linear bijection, then T inverse is also bounded. So this proved that it is a bijection. Lambda I minus T inverse is a bijection, it is linear, and it is closed, of course, since it is continuous, so it's be closed. So I can say that lambda I minus T inverse is also bounded, and that's all I wanted. When I say that lambda I minus T is bounded, so lambda I minus T belongs to LXX, then I can say that for those values of lambda belong in the resolvent. So this is all I wanted. When I chose the mod of lambda greater than norm of T, and I found out that in such a case lambda belongs to the resolvent set, because in such cases lambda I minus T inverse exists and it is bounded. So I proved the other way around, that sigma T is the values of all the set of all lambdas belong to the set of complex numbers such that mod of lambda is less than equals to norm of T. So it might be not just a single component, it might be two disconnected components also. So this is just one of the points I wanted to put across. And next we see that so I know that r lambda t, the norm of r lambda t can be written like this, can be represented like this. And of course this is a geometric series, so I can calculate it using the formula. And if I substitute lambda, as lambda tends to infinity, then I can see from this equation that r lambda t, the norm of r lambda t also goes to 0. And the third one is a good one. So as till now I have proved the first and the second one, and now in the third one I want to prove that if X is a non-trivial complex Banach space and T is a bounded linear transformation, then I want to show that the spectrum in such a case is not null. So how would I show that? So I say that suppose that the spectrum is null. Now since the spectrum is null, then the resolvent is entire, meaning that rho t is all complex numbers. Now, if such is the case, and I know that the resolvent, that is, well, if rho t equals to c, then lambda I minus t inverse is defined everywhere. And because of 2 and it is continuity, it is also bounded. So I know that holomorphic functions are continuous. And from 2, I know that functions which are continuous everywhere and decay to 0 at infinity are bounded. So I can say that this function R lambda, or which I can write as lambda I minus t inverse, is bounded. Now I know that I choose a L belong to x star and a x belong to capital X. And I say that this complex value function f lambda, which is written as L R lambda tx, is entire and bounded. So if this function is entire and bounded, so what I want is, I want to take another use of a theorem from complex analysis which says that holomorphic functions which are bounded everywhere are constant. Now I know that this is a holomorphic function, and I say, so I know that this function is holomorphic everywhere. And okay, so the Liouville's theorem tells me that if a function is entire and bounded, means that is holomorphic everywhere and bounded, then it is constant. Now it follows that we saw in the previous theorem that as lambda tends to infinity, R lambda of t tends to is equals to 0. So this limit equals to 0 when lambda tends to infinity. And thus I can say that as lambda tends to infinity, then f lambda must also be 0, so that f is identically 0. So earlier I said that okay, f is holomorphic and it is bounded, so it's holomorphic everywhere and it's bounded. So I know from a resultant complex analysis that f must be constant. And now I'm saying from the result I proved above that the limit as lambda goes to infinity of R lambda t is equals to 0, and thus I say that the limit lambda goes to infinity, f lambda is also equals to 0. So f is identically 0, it's 0 everywhere, because yeah, if you are constant and if you're tending to 0 for some, then you are 0 everywhere. So now I can say that for fixed x, we therefore find that this thing is 0. Why can I say that this thing is 0? Because I had a result as a corollary of Hahn-Banach theorem. It says that let this Z be a Banach space, then L of Z equals to 0 for every L belonging to Z star, which implies that Z equals to 0. So I can say that this thing is equals to 0 for all L belongs to X star must imply that R lambda Tx equals to 0. We got it from here. And for each X belong to capital X. Now it means that R lambda of T must be equals to 0. Now I go the other way around. And this contradicts the fact that R lambda T is invertible, which was my assumption. And thus I can say that sigma T is not equals to null. So I've proven my result. So a quick summary, what did I do? I proved three things. I proved that when X is a non-trivial complex Banach space and T is a bounded linear transformation, then these three properties hold, and I have proven them case by case. Now the first thing that I would like to talk about is the spectral radius of T. So I have X, which is my non-trivial complex Banach space, and T belongs to Lx. Now I define the spectral radius of my operator T as a supremum of the mod of lambda, such that lambda belongs to the spectrum. Now I know that mod of lambda makes this a continuous function, and I know that continuous functions defined on compact sets attain their supremum. So the maximum is equals to supremum. And I know that sigma T is a compact set because earlier on I proved that rho T was open, so that sigma T is closed, and it is of course bounded. So I can say that, yeah, that on continuous functions, so I can say that continuous functions on compact sets are bounded and they always attain their bounds such that supremum equals to maximum. And I can define this thing as the smallest circle in which the spectrum fits. So if this is the spectrum, the shaded region, then the lambda star is the smallest circle, is the radius in which the smallest circle in which the spectrum fits, or the biggest circle which touches the spectrum. You can put it either way. And this part, the remark essentially says that since sigma t is closed and bounded, hence a compact set, and mod of lambda is a continuous function, so that the supremum is attained. Therefore, there exists lambda star belonging to sigma t such that mod of lambda star equals to RT, which is the spectral radius. So this is essentially the idea behind spectral radius, and now I know that I had a theorem before in which I defined that R lambda t is given by this representation when mod of lambda is greater than RT. And earlier I had that this was true when mod of lambda was greater than equal to norm of t. Now therefore we have a stronger result here, since I know that the R of t is always less than equals to norm of t. Therefore this result is better. And so this is all I had to say here, that now we have a stronger result, since I know that this is applicable when norm of lambda is greater than RT, and before it was applicable when norm of lambda was greater than just greater than norm of t. But I know that RT is less than equals to norm of t, so this is a better result. And now finally, in the final section, I start with giving a idea about functional calculus. So let's start by talking about what it is. So earlier I always had this notion of sine of x or cos of x, but if I want to do things like sine of t or cos of t, and then I would need this notion of functional calculus, so that by functional calculus I can talk about things like sine of t, where t is an operator in Lxx. And so this is the idea: let x be a non-trivial complex Banach space and t being in Lx, and u be a domain in C which contains sigma t, and f from u to C be holomorphic function. Then we can define f of t with this integral formula. And well, let's start like this. So f of lambda, let f of lambda be given by a power series representations, and it means that f is holomorphic in a ball of radius r around 0 from C to C, and this is defined by a power series. And this power series converges absolutely for mod of lambda less than r. So I say that this power series converges here. Now suppose that t belongs to Lxx. Then I define f of t with this formula, and this f of t is holomorphic in this region, a ball of radius r, which is a subset of Lxx to Lxx, and the series converges for norm of t less than r. Because I can estimate this quantity, I can always estimate that this is less than this thing, and it converges if norm of t is less than r. And I am restricted to the ball in which I got the power series. So this is converging only, as you remember before, that in the condition of f of lambda, it was converging only when, if you remember, this condition was there, lambda minus lambda naught was less than r. But in this case, we take lambda naught to be 0. So this series is defined and it converges in this case. And similarly here, I define a functional calculus, and all those functions which can be represented by a power series, I can do, or I can define f of t of such functions with the help of this formula. So therefore I can talk about sine of t now, and this is all I wanted to cover in this section. And finally this remark, so f of lambda is given like this formula, is greater than lambda. So if the radius of convergence of the power series is greater than norm of t, which means radius of convergence of the power series is greater than norm of t, so capital R is greater than norm of t, then I say that this series converges and we can define ft as a sum. So this series converges if the radius of convergence of the power series is greater than norm of t. This is very important. So f of t can be only defined when the radius of convergence of this power series is greater than norm of t, and hence I can define f of t with this formula. And that's it for the video. In the final, okay, let's talk about this one final thing. So when I talked about defining functional calculus, when I define sine of t, or when I define things like that, I want them to satisfy my good old laws of calculus, this property of linearity, those properties of transitivity. So I want these three basic properties, linearity and communicative and transitivity, and all these properties, it should satisfy the f of t that are defined using the Reisz-Dunford functional calculus or by the infinite power series representation. So these are the properties that it should satisfy. Let's go through them. So X is a non-trivial complex Banach space, T a bounded operator, U be a domain in C which contains sigma t, and F, U be holomorphic functions defined from U to C, and it follows that they are linear. This property is satisfied and this is also satisfied, and hence we come to the end of our series on spectral theory.